Hi there, my name is Alex Komodo and I am a PhD student with the Applied Artificial Intelligence Institute at Deakin University. Today I'm excited to share my presentation at the ESEC FSC 2020 demonstrations track. Today I'll be discussing Threshy, a tool we designed to help set decision boundaries from outputs of machine-learnt components. Threshy has been designed to handle pre-trained classification models and is targeted towards the software engineer's workflow and not for the data scientist. As we'll see throughout the talk, Threshy is more than just a tool. The approach and workflows proposed in our paper serves as inspiration for generalizable model calibration designed for software engineers. To motivate our work, we selected intelligent web services as a case study, specifically those providing computer vision. Intelligent web services provide easy access of machine-learnt pre-trained classification models, which are abstracted behind cloud-based services. These services are becoming increasingly commonplace, since they do not require machine learning expertise or machine learning infrastructure to integrate powerful AI within developers' applications. These services abstract away all machine learning infrastructure behind RESTful web APIs, so it becomes very easy for developers without a dedicated data science team to build AI-first applications. However, the cost of abstraction means that many hidden assumptions exclusive to machine learning problems are no longer immediately visible. For example, the data used to train the cloud services is unknown, so developers are unaware of what patterns it recognizes based on its training data. We also don't know what algorithms are used to power these services, or what steps were taken to process the data into its model. Importantly, we don't know how the service's performance changes under different problem domains, since these services typically adopt a one-size-fits-all approach to be a generalizable model. All of these uncertainties become compressed as a single confidence value or score, which is returned alongside predictions made from its inputs given to the service. These services don't allow for much customization in the requests. Developers are typically restricted to one or two configuration inputs within their upload payload. The limited response payload means that developers have to work within the confines of parameters available within the response. In other words, the confidence score solely. They don't have insight into hyperparameter optimization, which is available to the service vendors behind the underlying model. And therefore, developers can't tune this model to their problem domain. Typically, evaluation procedures are performed to make client applications compatible with these services through decision boundary thresholds, given the confidence scores returned from the service, as this decides whether or not applications will take action from the prediction from the service. However, to fine-tune these models from output scores, developers need some way to calibrate associated inputs using a test dataset. Arbitrarily setting any threshold is not a sufficient means to confidence threshold selection. Multiple models have varying decision boundaries. For example, a model to detect email spam from Safe Email or HAM can result with a clear threshold of about 0.2 for the first model and another of 0.65 for the second model. One threshold for both models would result in misclassification. Furthermore, appropriate thresholding considers many cost factors beyond the model's performance, such as financial cost of decisions, the impact incurred due to wrong decisions, or maintenance implications. Currently, developers can write ad hoc scripts and adopt trial and error to find appropriate thresholding, but these scripts can become bug-prone, nor are they scalable. Furthermore, this often requires appropriate statistical training and expertise, and expanding threshold optimization to multi-class classification complicates this even further. To help alleviate this gap, we developed our own threshold tuner. We call it Threshy. First and foremost, Threshy is designed for software engineers without any data science expertise required. While Threshy is a tool we implemented, The overarching conceptual workflow behind Threshy can be adapted to generalizable model calibration. Ultimately, our aim is to help upskill software engineers to optimize threshold boundaries where the internals of a model are not exposed, in the case of intelligent web services. And, unlike existing tooling, Threshy is not intended for hyperparameter tuning. Threshy is designed to put the problem domain front and center of the threshold optimization process. Developers can visually explore varying confusion matrices by modifying global thresholds, or fine-tuning individual thresholds whilst considering different cost factors. Developers also benefit from automatic optimization, since Threshy can propose appropriate thresholds considering these cost factors via genetic or Bayesian optimization, making the process far more productive. Threshy outputs threshold configuration files that can be slotted in and out of the application domain at varying stages of development. This helps developers select decision boundaries without having to change any code, and given that Threshy can be used in post-development in a production environment, it can help identify when substantial changes from the service's model occurs. Lastly, Threshy supports a reproducible 8-step workflow that can be adopted entirely without the use of the tool, since our paper advocates for this workflow in development. Further, you can tune thresholds for binary, multi-class, and multi-label problem types using Threshy. You can learn more about this workflow and how Threshy deals with different problem types within our demonstration video. Threshy is an implemented example of our threshold tuner component, which we're presented in our complementing ESEC FSC 2020 Architecture Tactic publication. So for more information about the wider context on Threshy, please feel free to give this paper a read or watch our associated videos. We'd love for you to try out Threshy for yourself on your own problem types, so please visit bit.ly/a2i2-threshy to see more, or have a look at bit.ly/threshy-demo for detailed walkthroughs on how to use Threshy. Threshy is made completely open source on GitHub. We'd really welcome any feedback, so please visit the repo at github.com/a2i2/Threshy. So thanks for learning about Threshy. I hope you enjoyed watching this video, and we'd love to see what you think about the tool or the details behind Threshy within our paper. We look forward to your feedback. Thanks.